Can we get the lights just maybe, no, that's too much. Is that okay? All right, sorry I'm late. Two excuses. First one was that I was giving an exam and I tried to give my students as much time to finish that exam. And then I made up your test yesterday and I wanted to talk about it a little bit and I forgot it on my desk, so I had to go grab it so that I could know what I'm talking about. So it was kind of for you that I am late. So let's talk briefly. You might want to write this down because I'm not going to give you there's no like formal review or anything like that. But the test turned out to be 7 problems. Now, the section where the test starts is trig substitution and trig integrals. So that was where you had like the cosine to power, sine to powers, secant, tangent, all that stuff, right? Yes? I don't think so, not on this one. It's 7 problems, you got to do them all. Yes, there will be a bonus. Now, in that section with the trig stuff, remember when we did trig substitution, that often it turned out to be like cosines and sines or tangents and secants. So you're just going to have one problem from that section. Because in a trig substitution, you have to do the trig integral. You know what I'm saying? Like it breaks down at the end to be like secant squared or tangent or cosine. So one problem should knock out that entire idea, the entire concept. Partial fractions, of course, you're going to need to be able to do. What's that? Yes, the one that we're going to have on Tuesday. And then improper integrals. There were 2 types of improper integrals. There were integrals where your limits of integration went to infinity, or where inside the integral you had a discontinuity. And those are 2 distinct types. I'll give you one of those. I'm not going to tell you which one, but you'll have one from there. Then you'll have the next section would be finding the area between 2 functions. And that could be a function where you have 2 functions, f and g, and you're trying to find the area between them. Remember that anytime you're trying to find an area between 2 functions, you often have to find the intersection of the 2 functions. So be prepared to solve an equation when you set them equal. And as far as whether or not you'll be doing vertical rectangles or horizontal on area, again, it's one or the other, right? It's either going to be f is on top of g, or you're going to have to turn your head and do it the other way. So the integral is either going to be with respect to x or y. Okay, number 5 is, I guess that's pretty much what I'm saying, yeah. Number 5 is a multiple part question. It's 5A, B, C, D. And I'll just tell you a little bit about what it's asking for. Finding the integral without computing it, all right? Finding just the integral, the setup, for a region that's revolved around 4 different things. So it's the same region wrapped around, you'll probably have to wrap it around something horizontal, and you'll probably have to wrap it around something vertical, and I may move those things around. And I instruct you on one of them, you must use shells. I tell you have to use shells. And actually, it's a lot easier if you use shells. So for parts A, B, C, and D, 4 wraps for volume. Does that make sense? Okay. Then you have an arc length problem and a surface area problem. That's it. Time will be an issue, so make sure you show up on time. Be ready to go. I'll be on time. all those problems that I say set up but don't evaluate, you can take home. Now, it won't be a huge part of the exam. Maybe 10 out of 100 points will be what you do when you go home with it, but it's still something. So I expect you to compute all the integrals except number 5, where I ask you to wrap them. Those are just setups. Okay, let's move on. All right, what we're going to do today is we are going to do a couple of applications of integration of these integrals, and then we're going to move into the next chapter, which is sequences and series. If we can get going on it. It just depends on how long these applications take us. So the first thing I'm going to talk about is a famous paradox called the paradox of Gabriel's horn. And this isn't really an application, this is just an interesting result. It's not something where you would ever really use this anywhere, but it's kind of an odd sort of thing that happens here. First of all, we're going to start with the function f of x equals 1 over x. By the way, I'm very likely to pull a bonus question from today. All right, that's where I plan on pulling it. If we're going to have a bonus on the test, it's going to come from today's stuff. Gabriel's horn. So take the function f of x equals 1 over x and look at it on the interval 1 to infinity. So I'm going to graph it over here. 1 over x, let's see, at 1, it's at 1. And then as you go to the right, it kind of tapers down towards the x-axis. There's an asymptote there. It gets closer and closer, never touches, right? That's 1 over x from 1 to infinity. So here's the paradox. What we're going to do is we're going to rotate this thing around the x-axis. And we're going to look at its volume, and we're going to look at its surface area. Those are two different integrals, right? So let's first look at the volume of this. If we wrap that around the x-axis, the volume will be what? Pi times f of x squared. Good. So in our integral, we'll go from 1 to infinity. So if you need to kind of blow this graph up a little bit so you can see what's going on, all we're doing was taking a rectangle like this, right? That's all. We're taking a bunch of those rectangles, adding them up. The top function is f, and then the bottom is 0, or there's really no function. So there's no difference of functions, just function on top. So the function squared, what would that function squared be? 1 over x squared dx. That's it, right? That would represent the volume of this thing as you take it out all the way to infinity, right? Now, let me draw the picture of it rotated. If you rotate that around the x-axis, doesn't it look like this? And it goes forever, but it's like a horn, like a, right? That sort of horn, not like a horn in a head, right? It's Gabriel's horn. I think Gabriel has to do with like, I don't know, is Gabriel like Satan type stuff? I don't know, or like angels, something. It's related to angels or devils. I don't know. Is that what it is? Okay, so it's Gabriel's. It's his horn that he plays. Whatever. That's the paradox, or that's where it comes from. So this is this infinite horn, right? Now let's compute the volume. All right, I actually want us to compute that integral. Remember, this is just x to the negative 2, right? So the antiderivative of x to the negative 2 is what? Negative 1 over, careful, antiderivative, negative 1 over x, negative 1 over x, right? So this equals pi times negative 1 over x, correct? That's the antiderivative. Evaluated from 1 to infinity. You all with me? Okay, now let's plug in infinity and 1. When we plug in infinity, we get pi times negative 1 over infinity. But remember, infinity was the idea. So what happens is the denominator here goes to infinity. That'll go to 0, right? Negative 1 over infinity goes to 0. So that goes 0, kills off the pi. Everything goes 0 there. Minus, now in the other one, I'm going to plug 1 in. So pi times negative 1 over 1. That's just negative 1, which is negative pi, but then you're subtracting. So this is just pi. So Gabriel's horn has a volume of pi. It's kind of odd, isn't it? The thing goes forever, but it has a finite volume. All right, now let's look at its surface area. So what was the formula for the surface area? We had that last class. It was 2 pi. I'm just going to write the formula first. It was 2 pi a to b, and then it was the function times the square root of 1 plus the derivative of the function squared dx. That was what we got last class, right? So I'm going to need the derivative of the function. I may as well get that now. My function is 1 over x, which is x to the negative 1. The derivative of that is negative 1 over x squared. And if I square that, I get 1 over x to the 4th. Agreed? So my area will be 2 pi integral from 1 to infinity. The function itself, which was 1 over x, inside 1 plus 1 over x to the 4th dx. Everyone agree with that? Now that surface area formula right there is something that I would expect for you to be able to do on a test. So what was the technique here from last class? We only did one, I think, that we computed the whole way. Common denominator inside the square root first, right? See if that helps at all. I need to go to a new page. It was, area was 2 pi integral 1 to infinity 1 over x square root. Common denominator should be x to the 4th plus 1 over x to the 4th dx. Right? Any ideas here? Okay, so let me do this. Let me come back and let's just work on this integral here. Just the integral. Forget all the 2 pi and the limits and everything. Is that what you're suggesting? That fraction inside the square root can be broken up into 2 fractions? Right? You agree with that? So I could pull that 1 over x squared out as, well, let me do it this way. Square root x to the 4th plus 1 over x cubed dx. Now what? All right, if the inside of this is u, if the inside of that is u, then du is 4x cubed, but it's in the denominator. That's a problem there. Trig sub, we would have to have x squared plus a squared in there.
We can put x to the squared x. You can do x squared squared plus 1.
You could do x squared squared plus 1. However, let's see. You're suggesting x squared squared plus 1 over x cubed dx. But then, so you would have to, basically you're trying to turn that square root in there to u squared plus 1. So you would have to make a substitution that u is x squared. Do you all agree? U is x squared? Partial, no, because we have the square root.
But if it's a u is x squared.
You want to try u is x squared? My plan was to give this to you for a take home, but we can keep going.
Yeah, I can give it as a take home.
Do you want it as a take home?
Yeah.
Okay. Let me see. If u is x squared, du is what? 2x dx? You don't have a 2x dx. Do you? No. Now, you could make it happen, perhaps. Anyone see anything else possible? Okay. I took this right here and I split it into two roots, like this. So when you have a fraction inside of a square root, you can break it up into two square roots, and the square root of x to the fourth is x squared. That's right. No, I don't have to. Well, I have to keep the square root there. But see, anytime you have fraction in a root, you can break it up into two roots separate. Any other integration by parts on which one?
The square root of x squared plus 1, make that.
All this here?
Yeah.
So possibly. So here's what I'd like for you to do, and I'm going to offer this as a bonus, all right? Finding the volume was pretty straightforward, right? And we found a finite volume. The paradox for Gabriel's horn is that the surface area is infinite. That means it diverges. So as a take-home bonus to be turned in next class, just work out this integral for surface area. Show that it's infinite. All right? So a bonus is to finish this. Show the surface area is infinite. And do you see what the paradox is in that? Yeah, like just imagine you had this horn, right? It's saying that if you turned it upright and you could fill it with a certain amount of paint, right? Pi gallons or whatever it is. But you can't paint the surface because the surface is infinite. It's kind of odd, right? Anyways, okay, you can research it yourself. I just want to show you that kind of strange problem. Let's see. How did that get down there? All right. Now let's get on to a real application of integrals. Hydrostatic pressure. I'm sure we've all been in a pool or somewhere before when you swim to the bottom and you feel the pressure on your eardrums, right? The deeper you go, the more pressure there is. That's called hydrostatic pressure. And it turns out that there's a couple of things I'm not going to be here to prove. I'm not going to be here today trying to convince you of this. We're going to just take these as facts. And what I'm trying to get you to see is that when you get to like engineering courses or physics courses, a lot of times there's a physical problem and the physical problem turns into an integral. And so the question is, can you do the integral or not? And part of the problem will also be turning the word problem into the math, so how do you convert it, the words into the math? So let's just take a couple of things first on faith. That is, number one, fact that at any point in a liquid, the pressure is the same in all directions. So if you take, whatever it is, if I take this bottle right here and I hold it underwater, let's say, I'm holding it, let's say there's this big swimming pool and I pull it under, then the pressure at every point on this object is the same, all right? And the pressure comes from the water. Now, that's the first thing. The next thing we need to know is if we're talking about water, H2O, right? Then there are certain values for its what's called weight water density. So if you take a cubic foot of water, it's basically going to be applying 62.5 pounds of force. Right? So that's another thing. I mean, that can be measured. And now if it's a different liquid, then it's a different water weight density. With me? All right. A result of this is that the pressure on something in any direction at a certain depth. So I mean, we know if we're just like 1 foot underwater, we don't really feel it on our ears. But if we go down, if you've ever been down to like the bottom of a 12-foot pool, anyone ever been down the bottom of a 10 or 12-foot pool? I mean, you start to wonder whether or not you should keep going down there, right? Go down there and you feel it. So the depth has an effect, and it's because all the mass of the water above you is applying pressure. So what we have is this. The pressure is going to be the water weight density. If you're in water, it's the water weight density times the depth in feet. Now, I'll point out that the book in most physics classes, if you've ever taken a physics class, you're always having to be concerned about your units, right? Sometimes it's in meters, sometimes it's in feet, right? Sometimes it's pounds, sometimes it's newtons. So we have these different measurements. I'm going to do everything in here today in feet and pounds, just because I think it's something we know, like 100 pounds, like we know how much that is, right? Or if I say 100 newtons, you may not have any real concept of what that is. Yes?
What is that symbol?
What's what? Anyone know what that's called? This one right here? Ooh. Where are my Greek alphabet people? No? All right. Like I said, I may take a bonus question from this today, so I'll let you do research on it. Learn something. It's be careful. There's a delta. Delta. Okay. It's written different ways. I want you to go in and look up your Greek letters and see which one they always use for water weight density, because they usually use the same one. Don't confuse it with this, though. This is D. This is D for feet, okay? So Greek letter here that we're going to leave unknown at this point. Okay, but pressure is that water weight density times the depth. If you're in meters, it's different. It's not 62.5, all right? You have to do, it's 1,000 times 9.8, which is acceleration of gravity. And so, but it's different. And if you were in a physics class, you would see them and they would use a different number there if you're in meters. Fine. Book does it. You can look at that yourself. So the pressure in any direction at a point somewhere D feet deep is going to be that. So at 1 foot deep, it's what? 62.5 pounds. It'll be pounds per square foot. And then you keep going. You can do 2 feet, 3 feet, whatever. Now the force is pressure times area. Now this comes from, there's different formulas for this. Pressure, sometimes people see this one first, is force divided by area. The pressure you exert on something is the pressure is the force divided by the area. Or you could do area is force over pressure. That, you can move these things around any way you want. But our force is our pressure times our area. That's the one we need to remember. All right? That's what we need to move forward. I want to see if I can make this make sense at all. What's the difference between force and pressure? I mean, like, can you explain it in a way that would make sense to average person out there? Okay. That doesn't help my normal person out there. Doesn't help my sixth grader. Okay. If I take an elephant, right, and I put him, he has a certain weight, right? That's force. The force is his weight. Now, if I have the elephant stand on all 4 feet, right, then his weight is distributed over the four of his, I don't know what you call the bottom of an elephant's foot, but over his 4 feet, right? So you could say it's almost like divided 4 ways. So there is the pressure is that force over the area he's standing on, the surface area. So if he stands up on 1 foot, like elephants can do that, right? Then all his weight now is on a smaller area. So the pressure is much greater. So that's why if you look at this right here, pressure is force divided by area, right here. If I take the area and decrease it, that fraction gets bigger, doesn't it? Decrease the area, pressure increases. I increase the area, pressure decreases. Which is why when you're in the snow, you wear skis, because your weight is distributed over the area of the ski. You try and stand in your bare feet in snow. Now all your weight's concentrated over a small area. Pressure increases. You go into the snow, right? I mean, that's the relationship. So that's where this comes from, and now we're going to use it to compute a total force. So the idea now, what we're going to compute is this. If I take something and put it underwater, I want to know how much force is being applied by the water on that surface. And we start, and the only thing we're really going to do in this class is take something like a plate. Just like, imagine like a 2-dimensional plate. When you put a 2-dimensional plate into the water, really, there's a force at every point, right? So there's a force on the side, and then there's a force on the other side. And so those forces almost just cancel each other out. What I want to know is what's the force on one side of the plate? Which would be different from the bottom, different from the top. It would depend on, different in the sense that the area determines that. All that determines is the area. And the depth, yes. So let's look at this first plate we have here. I have the blue is the water level, okay? I take a plate, which is a 4 foot by 6 foot plate. I submerge it 2 feet underwater, so the top edge of the plate's here. I want to know what the hydrostatic pressure is, hydrostatic force is on one side of the plate. And then it's the same on the other side, and they're canceling each other out, right? But just on one side. And then what we could imagine later is that this is a box underwater. And so you have the forces, on sides, and you could look at all sides, right? Make sense? All right. Now, think about this, though. The force, I'm going to do these like little bands. Let's say I take this highlighted green band. That green band has a certain force on it because it's a certain depth, isn't it? Yes? But if I go a little deeper to, let's say, another band like that, then that is going to have a different force on it because it's a little deeper. And then as I keep going deeper, the force keeps changing, right? So what I'm going to try and do is find the force on each band and then do an infinite number of bands. So it's like an integral like we've been doing, right? You're trying to find, pardon me? It's not an average pressure, it's a total pressure. It's the total force is what it's going to be. But to get the total force, we're going to look at the pressure. To get the total force, look at that equation up there. To get the total force on this plate, we're going to look at the pressure being applied on each area, right? It's going to be the pressure times the area of each band, and then do an infinite number of bands. Cut them up into smaller pieces, add them up forever. Understand the idea? Why can't we do what?
Just like because we have the plate,
Uh-huh.
the length, the base, or the width.
To find the area? Well, that'll give us the total area of the whole plate, but then you're supposed to multiply it times the pressure. And the pressure is different at every, different depth. So the pressure at the top of the plate's different than the pressure at the bottom. So that's why you can't do it just as a total. Make sense? That's what we're going to try and do geometrically. Geometrically, that's what we're trying to do. So I'm going to take this real quick, draw it again. Here's my plate. It was 6 foot, 4 foot. It was 2 feet deep, right? All right, so I'm going to draw now an X, and well, not even an X and Y axis. I'm just going to create an axis. All right, there's my axes. I'm going to orient my plate to be one corner of it is at the origin. So it is 6 wide and 4 down. Now, I'm also not going to really even count that 4 as like a -4. I don't want you to look at these as really axes right now, okay? Just look at them as I'm trying to orient my, my plate somewhere. So I can measure from the top left corner is where I'm going to measure from. 6 out, 4 down. All right? Now what? Well, you know what? Hold on a second. I didn't include the depth. Hang tight. I didn't include the depth. That did have depth, right? I forgot which problem this is. Was it all the way at the water surface or not? It was too deep, right? Okay. It was too deep. We're going to put it too deep then. Like this. Let's orient it like that. So then it would go from 2 here to where? 6 there. And that's 4. Okay, now let's take a slice, a horizontal slice of this plate, and it's going to be an arbitrary slice. So it's one of those bands that I was talking about. I'm just going to pick a random band, and I'll draw it like this. I'm going to call the distance from the water surface down here. I'm going to put my little blue water up there. The distance from the water surface down to where I picked my band is X. Yes. Yep.
Is drawing the arbitrary rectangle necessary?
Yes. Yes. If it were a bonus question, I would expect you to draw me the region. All right. That okay? We want to know what the area of that arbitrary band is. Because remember, the formula we're trying to work with is the force is equal to the pressure times the area, and I need the area of that little band. So how wide is that band? It's 6. It's always 6, isn't it? I think I'll blow my band up over here. It's 6 wide. And then how tall is it? D, we're going to say dx because x was my measurement, okay? That's why you don't necessarily have to, your x doesn't always have to be x-axis. Your x can be anything. I could have called that L, I could have called it D, H, it doesn't matter. It's just the measurement from the surface to that band. So, but because it's going to change and I'm going to have an infinite number of them, that'll be my infinitesimal dx, the way it's always been. So what's the area then of that little band? 6dx. All right, now let's try and get pressure. Because all I need now is pressure, right? The pressure, we said, was that Greek symbol that... Okay, it's not a bonus question anymore. Delta what? D? Delta D? Now delta is going to be our weight water density for, right? For water, it's what? 62.5? Now you don't need units right now. Just put the number. And then D is what? the depth. What's the depth of this strip? X. Right? That's because at that strip right there, our depth is X. And that X changes, doesn't it? So now what I'd like to do is talk about the force on this one little band. What's the force on that one little band? Yes? No, because my X is measured from the top of the water down to where my band is. So it's the total distance. I didn't measure from 2 down. It would be 62.5x times 6 dx. It's just P times A. Everyone see that? What's 62.5 times 6? 375? 375 x dx. That is the force applied on an arbitrary band of this plate. And now what I'd like to do is what? Add all those forces up for the entire plate, which means I want to do an integral that goes from where to where? Careful. From 2 to 6. From 2 to 6. Because X is my depth, right? And that depth, if you look at it, my X, yes, it could go all the way to 0, but my plate starts at 2, and then it goes down to 6. So 2 to 6 of 375 x dx. You can pull out the 375. It doesn't matter. You're going to divide by 2, right? Because the antiderivative, that's 1/2 x squared. Okay, so we're done, right? At this point, let's just get an answer. I don't feel like doing it. $6,000. It's total pounds. Pounds of force. It's 6,000 pounds of force over that entire area. Nope, just one surface. This is a 4-foot by 6-foot plate that is submerged 2 feet underground. The force on one side of that plate is 6,000 pounds. Now, of course, the force on the other side, 6,000 pounds also, and so it's not, not going anywhere. 6,000 pounds over the entire thing, though. So 6 by 4, really, right? 6. Oops. That's what I was going to look at. Times 72. I think I'm getting that same thing. Hold on. 1.7, is that what you said? Yeah. It's so yeah, this is so basically you have 1.7 pounds per square inch, which is really not a whole lot. Well, that's right. This is physics. This is engineering stuff. But it's application of integrals. That's all it is. Yes. It was 3 feet? Uh-huh. 3 to 7. Yep. And of course that's going to change everything, right? Because now your plate's deeper and, Does this make sense though? I hope again this also ties in the whole idea of the Riemann sums. The importance of taking something physically and breaking it down to adding up these things forever. That's all the integral's about. Let's try another one. Okay, how about this one? We have a different plate. So this plate is triangular. I'm actually just going to put it underwater so that just the tip of the plate is touching the top and then the bottom. And I'd like to know what the total force is, hydrostatic force, on one side of that plate. One side. Same thing. It's just, it's one side, the force is the same on the other side. Well, this isn't a right triangle, so not necessarily, but possibly. That would be a question. Would it be just a ratio of what you would find? Like if it was a rectangle, would this answer just be the ratio of the area? Would the ratio of the force be the ratio of the area? What do you think? That's right. See, the force, think about how much of this triangle is below deeper, right? So that wouldn't necessarily, okay, so that's something you could resolve yourself. And in general, look, we're working with rectangles and triangles, but we could have something more oddly shaped underwater too, like our next example. But let's just do this one first. So I'm going to go ahead and start this one out. I'm going to draw everything again. So here's my plate. Something interesting to kind of point out right now is that we're talking about the depth of the water, but we're not talking about how wide this tank is, right? You know what I'm saying or no? Like, if I have a plate in the water like this, then let me just draw next to this. This is my tank drawn in three-dimensional. Okay, this is my water level in here. And then my triangle's down in there like that. Does it really matter how wide my tank is? That's right, pressure is the same. So my tank could be 2 feet wide, and I put my plate in there, or it could be 100 feet wide, and it's going to be the same. That's very interesting, because think about a dam holding water, right? A dam holding water. All that water fills up behind the dam, and you have all that water behind it, right? The hydrostatic pressure is not determined by how much water is behind it. That's kind of interesting, isn't it? Now, I mean, assuming it's flat. I mean, if you have this and you put a dam down here, then of course, if you put, a little bit of water here, it's not as much as if it was. So, assuming it's flat, because what happens is all that mass over there is basically the Earth itself is taking that weight. The force of the Earth is countering that. So, I don't know if that makes sense, but straight down. So the ground counters it, and so it doesn't matter. All right, let's try and do this one. I'm going to set up some arbitrary axes. I'm just going to orient them like normal. I'm going to draw my triangle. I'm going to put my triangle right. I'm going to try it by just putting it right at the tip like this. And my water level's up here. I'm going to come in here with an arbitrary rectangle like this. I'm going to say that I measured from the water down, that was X. Can you tell me how wide this thing is? This rectangle. The width of this, doesn't it depend on where you are? Like where you pick that? So what you need to do is find a relationship between where you are and how far you go out on each side. So let me try and draw this picture again over here for you. It might help. If I say this is X, right? And I have one side of my triangle is coming down like that. My question is, what's the distance from here to here? Do y'all see I'm just looking at this part right here? Is it half?
Depends on
Well, but we're not. We have a little more than just like we're not drawing it arbitrarily. This thing has dimensions, doesn't it? How long was our triangle total? How deep was it? 5. And then over here, if I'm just drawing half the triangle, it would be 2, right? So the question would be, what would this distance from some arbitrary point over here be to here? If I call that, let's say, W. Aren't those similar triangles? You don't need the angle. Does everyone see we can set up similar triangles? We could go like this. We have a small triangle, and we have a big triangle. Big one is 2 and 5. The small one is W and, I don't know, X. Yes. It's not just anything. It's X, isn't it? So you can set up the ratio. X over W is the same as 5 over 2, which means that I'm trying to solve for W, right? 2x equals 5w, which means that 2x over 5 equals w. Now that's one way to do it. The way that I did it, the first time I ever looked at this problem, was I said, look, I've got back here on this thing, on this drawing I have on the side, I said that's a line. And it has a slope of what? So turn your head sideways and look at it like a graph. You come out x, right? So that line has a slope of what? Rise from the origin, go up 2 and then over 5. So it has a slope of rise over run, 2/5 x, and a y-intercept of 0. So that distance would be 2/5 x. It's the same exact thing that you get when you set up a ratio of triangles. Either way, you get the same thing, okay? Now, that's just the width. Going back up here, this width, W, is just this right here. So what's the width of our entire strip? Twice that, right? Twice that. So 4x over 5. All right, let me try and put this together down here. The area of our little strip right here, we said that this was dx. Well, we didn't say that, but we know that from last problem. We know that this will be twice 2x over 5, so 4x over 5 is how wide it is. And so the area is 4/5 x dx. What do I need after I get the area? Pressure. The pressure is delta D, which is 62.5 times D. Now, what's D for us here? Going back up to our picture, it's the depth from the surface to our rectangle, but that's what we called x. So x. So then the force would be PA. So 4/5 times 62.5, right? I'm going to go ahead and do that. Is it 50? Yeah, 50 x squared. And now we need to get the whole thing, add all those rectangles up. So the total force, the solution to the problem will be the integral, 50 can come outside, where to where? Where does x go from here? The top of the rectangle is 0, isn't it? All the way to where? The bottom? I mean, rectangle. The top of the triangle is 0, and then the bottom is 5. So to go from 0 to 5, x squared dx. We are not going to look at this as an xy axis. We're just going to look at it as arbitrary values. Like we could be turning our heads this whole time and be orienting right? If I turn my head, then this is the x-axis like this, and I'm going from 0 to 5. The only reason we are actually looking at it this way is because it's in water, and we always look at down as being this direction, but 0, 5, we should get 2,083.3 pounds applied on the entire thing. All right, last one. Ready? Can I move on, or? Let me just move that. These got out of order. You know how I usually put the notes online? Just so you know, if you go to print these out or look at them later, I had worked these problems out already before class. So you're going to see the solutions I did before class and then the ones I'm doing today. So you'll see like duplicates, just FYI, so you know. All right, here's the next one. Let me see, 36, 12, and 2. 36, 12, and 2. 36, 12, and 2. So let's say we have a dam that has a wall that's 36 feet high. The water level right now is 2 feet from the top of the dam. And we have one of those, I don't know, what are they called? Release gates or something. It's a semicircle. It's a half circle that they will open that door and release water so that the dam doesn't overfill, right? Floodgate or something like that. So it's a semicircle at the bottom of the dam. And let's say that this thing has, from one side to the other side of this semicircle, let's say is 12 feet. You know what? Yeah, that's good. 12 feet. The question is, what's the hydrostatic pressure, or what's the hydrostatic force on the door? The force, the total force being applied on that door. Because you want to make sure that that door can hold, right? So you better know how much force is being applied on it. Well, we need to draw something, right? Get some things oriented first. How about I start with some sort of rectangular axes? Where would you like to draw this circle? Where do you want the water level? I mean, it's your call here. Does the actual 30... Did I forget to put 36 feet, or did it disappear? 36 feet was supposed to be here. That's the height of the wall of the dam, and then I had 2 feet for the depth. Does that 36 really even matter? No, it's really 34, right? It's really the depth of the water is 34 feet. So we have different ways we can actually go about this. One approach would be to do this. Oh, there it came. See, it came back. I don't know. It's weird. You want to try by just putting the circle at the origin, semicircle at the origin? We'll try it. It'll look something like this. Not very good, but there it is. What is the radius of this thing? 6. So this is 6. And I know that my water level is somewhere up here at what? 34. That all right? Let me draw an arbitrary rectangle in here. There's some things I can get already. X, okay, where is X though? Be kind of careful with this. You want to measure from where to where for X? You want X to go from water level to rectangle? What do y'all think about that? That's X. Look at where you oriented the origin here. Yeah, if I'm going to measure out from somewhere, see, I oriented myself where the center of the circle was at the bottom of the semicircle, right? The center of my orientation plane is at the center of the circle. So I need to measure out from there. So my measurement needs to be from here as I turn my head that way, right? So from 0 to there, what do you want to call it? Call that X. This right here is X. And then the distance from here to here would then be 34 minus X. Wouldn't it? See, because you need to know the depth in the problem, right? The depth in the problem of that little sliver is 34 minus X. But X is the distance from the center of the bottom of the dam up to the rectangle.
How is that different?
Well, the other problems, where was our origin?
So it's just
The origin was at the... You could have set it up differently, yes. You could have put your origin at the water level, and then you could have measured X down to it. I don't know. Try it. I'm just showing you there's more than one way to set up these problems. It's not going to be exact. You always make the water level your origin. It's not necessarily always the case. Here's why. Because I need to know here's why I put it where I put it. I need to find a relationship now between X and how wide that rectangle is. Right? How wide is this thing going to be? When you're at an arbitrary place, how wide is it? You know, you start at the bottom, it's 12, but as you move up, it gets smaller and smaller, right? So as X changes, your width changes. Well, that has something to do with area of the circle itself, or semicircle. Okay, let me try and help you. Let me draw something for you. Let me draw a circle radius 6 for you. If I come out here to some place X, and I want to know the distance from here to here, right? Isn't that going to be basically the same thing as the distance from here to here? Yes? Yeah, that's like the y coordinate. It's like I have the x coordinate, I need the y coordinate, right? What's the equation of a circle? Of my circle right here. X squared plus y squared equals r squared 36. Can I solve that for y? Yes. Solve it for y. Take square root. Y equals square root 36 minus x squared. Right? Now, that's why I oriented it at the origin. That's why I oriented my circle where I did. Because if I had made that the origin up there, the equation of that circle would not be this. It would be what? X squared plus y, and then you have to shift it down. The center of that circle would be down at where? Negative, right? It would be 0, but then it would be negative 34, wouldn't it? So this would turn into y plus 34 in parentheses squared. So then you solve for y, it'd be just much more challenging. you see how that helped dictate where I put the origin? Okay, so that would give us the width of the yellow, but we want the width of the whole rectangle, which would be double that, wouldn't it? Okay, so I'm ready to try and come up with a formula for my rectangle. Here it is. For the area, I have dx. I have twice that square root of 36 minus x squared, don't I? That would give me the area of that. So area is 2 square root 36 minus x squared dx. What is the pressure being applied on that strip? 62.5 times the depth. The depth is 34 minus x. Y'all see that? The 34 minus x instead of x. Questions? You ready for the force? The force on that strip is 62 times 5, 62.5 times 34 minus x times 2 times the square root 36 minus x squared dx. That's the force on that arbitrary rectangle. And then integral time. Add them all up. So where's your integral going to go from here? The variable is x. Look back at your picture. What is x going to vary from?
0 to 34. Could it go up a little bit?
You want your rectangle. You want your rectangles to start out. You want your rectangles to fill up that whole semicircle, right? Which means your first rectangle, let's just say, has to start at the bottom. Come here. At the bottom, which means x would be what? 0. X is this distance. And then it has to go up until you get to where? 6. Because it's a half circle and the radius is 6. So your integral will go from 0 to 6 of all that stuff. 125. I'm going to pull that out. That's the 62.5 times 2. And then you have 34 minus x square root 36 minus x squared dx.
This one looks really similar to the surface area. We put it to something like that, or not? Surface area formula?
Yeah, it's just coincidental that it looks that way. Notice we don't have a pi in there, right? Like there's, yeah, no. Now I'm going to have the calculator do this for me. I'm getting 111,116 pounds. 111,116 pounds. 111,000, sorry, 116 pounds. Which I'm getting I'm trying to get a pressure per square inch here. 6.8 pounds per square inch. That's just a real rough, I think I did that right. About 7 pounds per square inch. Oh, wait, I didn't divide by 2. That was the area of my circle, but I forgot. I did the area of the circle. What's the area of a whole circle of our door? It's pi r squared, right? The radius was what? 6 feet? I do 6 feet to inches first. 6 times 12, that's 72 inches. I square it, that's r squared, times pi, and then divide by 2. So the area of the semicircle of my door is 8,143 square inches. Then I take my 100,000 or so, where was it? Oh man, there's that, and divide it by that 8,000. Okay, 13.6, so almost 14 pounds per square inch. That's a pretty good amount of force. Yeah. Yeah. Just about. I mean, what are your tires in your car? Somewhere around probably 30 or so pounds per square inch. So, okay. Does this all kind of make sense? All right. It's pretty interesting that you can apply integrals this way. Now, the next application that I wanted to talk about is, let me see if I've got everything in the right place here, is center of mass. And I'm not going to really do a whole lot with this because we just don't have time. But I decided what I would do is, instead of spending a lot of time showing you center of mass and just telling you about a formula for hydrostatic pressure, I think hydrostatic pressure you have to see examples to understand. So center of mass, I think once I give you the formula, it's pretty easy. But let's talk about what it is first. If we take a two-dimensional, this is a two-dimensional lamina. That's what we call this, a lamina. So a two-dimensional lamina would be something like a sheet of paper. All right, we can just take this. Imagine that this is two-dimensional. So the thickness of the paper doesn't matter. And let's just make it some weird arbitrary shape. Like it doesn't even have to be rectangular anymore. There we go. There's a two-dimensional lamina. The question is, where is its center of mass? So if I were to take this and try and balance it, you know, obviously up here, that's not the center of mass, right? There is some point, and only one point, that would be the center of mass of this, where it would balance on that point, right? And the importance of this is that if every physical object has a center of mass, then when you get to physics, you can look at every object as a point mass instead of as some weird, crazy shape, right? Instead of looking as a car goes down a road, you look at it as a point goes down a road, and the point is its center of mass. So finding centers of mass makes sense. Now in Calculus 1, 2, what are we in? 2? In Cal 2, we are stuck with just a flat sheet of paper. But in Cal 3, you can extend this out to three-dimensional objects and finding centers of mass of the things that would make more sense in the real world. But we have to start somewhere, right? So we start with just the 2D case. We also have ways of dealing with whether or not this lamina is homogeneous or not. Homogeneous means, is the density of this paper the same throughout the entire page? Or is it more dense maybe over here than over here? You know what I'm saying or not? I mean, the material itself matters. You can still find centers of mass even if the density changes within the object. We aren't going to do that. We're going to imagine it's homogeneous, which means it's uniform density. Okay? So here's how we do it. Oops, sorry. Like I said, I'm not going to go through the development of the formula, and like here's why it is this way. I'm just going to give you the formula. So all of this is going to be on page, the one that we want is on page 407. And here's what we've got. If you have some region like this, bounded by two functions. We've had that before, right? And we call this region R for region. And it is a uniform two-dimensional lamina. Okay, so we take that right there, that little region in there, and we want to find its center of mass. Then the center of mass is first of all called, it's a point, right? We have very special symbols for it. It's X bar, Y bar. It's that point. It has an X and a Y coordinate, right? Here's a question for you. Does the center of mass have to live on the lamina itself? Not necessarily. Think of a boomerang. A boomerang, right? A boomerang, its center of mass does not live on the boomerang itself. Think of a donut, a circle, right? Where's the center of mass of a circle? In the middle, right? So if I draw this lamina right here, right, this washer, I say, where's its center of mass? It's right in the center, and that's not on the object itself. So you can have a center of mass not even on it, right? Make sense? Yes.
But like you said with the car, when you're checking it out, you're going to check the center of that, not the other part of it.
Well, on a car, your center of mass for a car could be in a space that the car does not physically occupy. So the center of mass in your car could be right above your center console, just a point right there. That could be the center of mass of your car, and that's not on the car. That's not part of the car.
But it's a point.
But yes, it's a point, but it doesn't have to live on the object itself.
The question is, with the boomerang, will it be a point or will it change?
No, the center mass of an object is always constant unless the object itself changes, unless it loses mass or something. So if you cut it, if you cut it off, or you throw the boomerang and it breaks in half, then of course it changes. Okay? All right. So here are the formulas. First thing we need to know is A. A is equal to the area of R. How do you find the area of R? It's the integral. I didn't put AB here. I may as well put that right. The area of R would be the integral A to B f of x minus g of x dx. So in order for you to even be able to find the center of mass, you first have to be able to find the area of the actual region. Okay, that's the first thing. Now, let me tell you what x bar and y bar are. X bar will always be 1 over a integral a to b of f of x, x times f of x minus g of x dx. So you'd have to be able to compute this integral to get x bar. So it's really like two integrals that you have to do. You first find the area. That's an integral. We've done those before. And then and that'll turn out to be a number, right? The area will be a number. 1 divided by that number times this integral. This is x times f of x minus g of x. This is almost the area again, isn't it? But with the additional x in there. And if anyone wants to kind of understand where that formula comes from a little bit, it's kind of like if you look at a seesaw, right? A seesaw works. You have a fulcrum, right? A pivot point on a seesaw, and what you imagine doing is when it's balanced, right? The mass on the left, mass on the right are the same. Then imagine taking something and an object, and then moving it out a certain distance. That distance from the pivot point is called x. And then the weight would be whatever the function is there. And to counter that, you would have to have it the other way also, right? But you could have it go out less distance but more mass. That x and then this is basically representing, x is like the distance from the fulcrum, and then the difference of the functions is almost like the mass. It's like distance times mass. And then for the y bar, like I said, I'm not here to describe these. The book does a decent job of it. So if you want to look, you can read through the book. It even draws a picture of like a fulcrum and a little pivot point and stuff. And y bar, I have to go to a new page. Well, I can put it right up here. Well, no, I'll do a new page. Y bar is equal to 1 over a again, integral a to b, 1/2, and then it's the function f squared minus g squared. So it's f of x squared minus g of x squared dx. So those squareds mean square the function, right? In the past, I've written it like this. But I'm just putting the squared there now. Okay. That's it. Those are the formulas. That's what you would need for center of mass. Now we have 20 minutes, which is in no way time to start sequences. So why don't I do one example of center of mass? And we'll try something fairly easy as far as the integrals are concerned. Find center of mass of lamina formed by region bounded by y equals square root of x and y equals x. Is this, I don't want to do the example in the book. If this is the example in the book, I don't want to do it. Hold on. I'm going to change it. I apologize. Leave the y equals x. Make this first one 2 minus x squared. Now, we are assuming that this is a homogeneous, homogeneous lamina. It's the same throughout the entire thing. I'm going to draw a picture real quick. Y equals x is here. And 2 minus x squared looks like this. Something like that. And so we want to know for this region, if I were to cut that out, try and balance it somewhere, where is that center of mass? The book also refers to this as the centroid. The centroid is like the center of mass. All right, so here we go. Let's define our functions. This first one up here, this one's going to be f. I should color code them here. This is f. G is this one. We need to find out where they intersect, don't we? So we can get the endpoints. So I need to know where these two hit each other. So set them equal to each other. That turns out to just be a quadratic equation, right? It's factorable. If it wasn't factorable, I'd have to use quadratic formula, wouldn't I? So negative 2 and 1 should be our solution. Should be our endpoints of our integrals. Negative 2 to 1. Questions up to this point? First thing I'm going to find is the area. All right? So to get the area will be equal to the integral from negative 2 to 1 of the top function, which in this case was 2 minus x squared, minus the bottom function, which was x dx, which is really just integral negative 2 to 1 of 2 minus x squared minus x dx. And that's just 2x minus 1/3 x cubed minus 1/2 x squared evaluated from negative 2 to 1. So that antiderivative is pretty clean, right? There's not a whole lot to that. And in an effort to preserve time here, I'll just get this on my calculator. This is 9/2, which is 4.5. All right, so you could just plug numbers in and get that, you think? Now what? You've got to get x bar and y bar. Okay, so I'm going to go to a new page. X bar, by definition, was 1 divided by a, integral a to b, x, and then f of x minus g of x dx. So that's 1 divided by 4.5, or instead of 1 over 9/2, it's 2/9. It doesn't matter. I'm going to get a decimal at the end, I think. Integral negative 2 to 1 x times. Now, f minus g we just did, didn't we? Wasn't that 2 minus x squared minus x dx? So all I have to do now is take that and multiply an x through before I do an antiderivative. So 2x minus x cubed minus x squared dx. This turns out to be 1 over 4.5 times, when you do all that, you should get negative 9/4. That's what that whole integral is, negative 9/4. Now that I'm seeing that it comes out to be a nice number, is it all right if I take this 1 over 4.5 and change it back to 1 over 9/2? Okay, let me change it back. Yeah, so 1 over 9/2 times negative 9 over 4, that's the same as 2 over 9 times negative 9 over 4. The 9's cancel, the 2's reduce, so negative 1/2. Guess we would have got the same thing had we multiplied out the decimals too. What's your question? 4.5 is 9/2 from before, earlier. And then y bar. So now we need y bar. Here we go. Y bar is equal to 1 over a again. So I'll use the fraction again because maybe we'll get lucky and it'll work. 1 over 9/2 integral -2 to 1 times 1/2. And now each of my functions squared. So my f squared, which was 2 minus x squared, got to square that, minus the other function, which was just x, and I've got to square that, dx. Questions on any of that? Where I got any of that? Let's see, 9/2 flips up, comes 2/9, and then hits the 1/2, and that just becomes 1/9. Integral -2 to 1. Expand this out. So I did my expansion, right? I did my little foiling on this thing. Got those three terms. I can collect some like terms together there if I want. Let's see, 4 minus 5x squared plus x to the 4th dx. All right, I'm going to just again save us some time by doing this on my calculator. Do I have any questions? Getting 1/9 times all that becomes 18/5, which is 2/5. So we have our center of mass, our centroid is -1/2, 2/5. Yeah, center of mass, centroid. Centroid means you don't really have to be talking about a lamina. Let me see here. I want to bring something up here. Gosh, we still have 10 minutes? I thought that was going to take a lot longer. Where did our thing go from -2 to 1? What was it? 2/5? It was -1/2 and what? 2/5? Oh, yeah, point. I'm sorry, I thought I heard you say something else. Solid. All right, so that's it right there. Does that seem reasonable? I mean, just by looking at it, does it seem like that would be reasonable? Yeah. Now, I've done this in class before where I've actually taken this and printed it on a printer and then cut it out and put it on a piece of cardboard and then stuck a pencil like right at that dot and it worked. At least it was good enough. I mean, my cuts weren't perfect, but it was enough to convince the class that it's true. Pardon? Mm-hmm. Oh, yeah. Yeah, check it out. You can actually do that. Hold on. There's no cardboard sitting around anywhere. I almost grabbed a piece of cardboard before I came to class. Yeah, I mean, I don't have anything interesting to throw through the classroom, but no one has a piece of cardboard, huh? Well, I don't want you to tear anything apart for it. You can do it with yeah, that might work. Yes, yes. I can have this. I'll try my best to do this. Anyone have scissors? No? I'm not throwing that. I don't have scissors. I don't know if that'll fly the way I want. Let me try this first. I'm trying to do this without hurting myself or someone in the class. I'm just trying to make some weird shape here. And again, not kill myself. There we go. All right, so this is a very weird shaped lamina. First thing I'm going to do is find its center of mass. It's easy to find the center of mass of something when you have it like this. The way you do it is you get like a thumbtack and you just stick it and let it hang, okay, like this. And then what you do is you draw a line straight down. So you could like hang a rope. Okay, so this is like tacked into the wall, it's hanging. Then you have a rope going through that tack. You draw a line wherever that rope is. Now this can be real rough, okay? There, and then you just grab some other point, tack it into the wall, and then do your rope, and then do it again. And then the more points you get, the more accurate you'll be. Okay, so we go through. So this looks pretty good for my center of mass. Okay, so I should be able to balance on there. I'm a little off because that was real rough. But do you see it's about right there?
The marker tips are like inclined.
Yeah. This would kind of be cheating, doing this way. Hey, close enough, right? But you see the point, right? So if you do that, now this is where I can try this. I'm going to try and throw this through the air. And as I throw it, I'm going to spin it. Okay, and watch it. Watch what the dot does. I don't know if you can see that over there, right? Did you see it? It should just look like the dot just goes straight up and straight down. Not straight up and straight down, but the dot shouldn't be wiggling around. I'll try and throw it across the class.
It's not totally centered, so. Yeah,
It'll look more like a parabola here, maybe. Yeah, it didn't work very good. But as opposed to if I were to draw, if I draw this dot over here, I say that's my center of mass. Then when I spin that dot's moving around everywhere. The one in the middle should just be like a point moving through space. Okay. Well, when I see you again, it'll be Judgment Day. Yes.
I remember a couple classes ago you said we might be able to bring an extra formula sheet for the exam.
That's pretty good. Actually, I'm glad you brought that up. Let's see. What do you think? You have all those formulas, right?
I'm good with those. Can I bring a unit circle?
We'll do this. You can have all the formulas that I said you could have, right? And then in addition to that, you can have one 8.5 by 11 standard sheet of paper, front and back, with formulas, steps, anything else that you want. Nothing worked out. No problems worked out. You can't have examples written down. Okay, so if you want to bring something with a unit circle, that's fine. If you want to make your own thing where it says, hey, whatever. Just, you can't work problems out. That seem fair? Okay. Have a good day. Have a good weekend. I'm sure it's going to be a real good weekend.